Okay, we're going to look at some volumes of revolution and how to find them using integrals. This is actually a volume of a surface of revolution, is how they'll say it in the textbook. I just didn't want to put this all up on there. We're just for short form, we're going to call them volumes of revolution. But the idea is they give you two lines or graphs of functions or something. Here we have most basic one, because this is sort of the introduction to the concept. We're just going to do a simple example, then we'll get more complicated. But they give you two graphs of functions, and they bound an area, right? There's some area contained in them, and then you spin that area, and this is what this pink, I'll make it the laser tail so I don't have to erase it every time. This pink thing is indicating. Oh, that's horrible. We can't really see that. Let's do this one instead. We'll stick with the pink. You spin it around some axis. Here it's the y-axis. That's what I've got here. This says the y-axis. You revolve it. That's why it's called a volume of revolution. And then it makes this solid, right? So this one is going to make this kind of cup with like this divot cut out of it. If you look at it, I'm going to attempt against my better judgment to draw this in from a sort of side and see what it looks like. This thing is going to be like that, right? It's going to be, wow, the perspective is off. Hopefully you get the idea. You can Google a nicer picture of it. The idea is that it's this thing which, yeah, I spin it around and I get this solid. And so I want to find the volume of this thing. And this is, wow, I'm already regretting drawing this. You get the idea, hopefully. How am I going to find the volume of this thing? So in class, they're probably talking to you about Riemann sums and everything and limits, and nobody ever understands this. This is like one of the most notoriously difficult things ever. People just don't get this. I didn't get this when I studied it the first time. It hurts your brain. We're going to see a way to do it that makes it just like easy, just simple, stupid, easy. By thinking about it in a slightly different way, which is not actually what's going on. I want to say before we start, this is not actually what's going on. This is like the math equivalent of a metaphor that we're about to do now. It's not what's actually happening. I have to say that because if I was watching this, if any instructor is watching this, like I would be there, they would be pulling their hair out if they think I'm actually telling you that this is what's actually going on. That is not it. This is a way of thinking about this, which is going to help us construct the integral. What's actually happening is Riemann sums and all the stuff you learn in class, but that's not a very dynamic sort of visual way of understanding this thing. We're going to see a way of doing it, which will let us sort of picture what's going on and happening in terms of visualization and dynamic movement and cool. You'll see what we're going to do in a second. Okay. How am I going to think about this? First of all, I have the picture here, and it kind of gives it away a little bit, but I didn't want to draw this in front of you guys because you just sitting there watching me do lines is boring. I need to find the points of intersection. With this one, it's pretty easy. They're going to be 1, 1, and 0, 0, right? The way that I would technically find this, I would say x is equal to x squared, right? Set them equal, and this gives me x is equal to 0 or x is equal to 1. These are the two options for this. And then you plug it into both of them. You get 1, 1 and 0, 0 as the points. So this is the first thing. We'll see more complicated examples of this. The second thing is, so now I know where I'm going to integrate from. I know the bounds of my integration. I'm going to go either along the x-axis. In this case, we'll go up the y-axis. We're going to go from 0, 0, or from in just the y direction. We're going to go from 0 to 1. That's y is equal to 1 up there. And what we're going to do, the way we're going to do this is we slice this thing. You've probably seen this. We slice it at any point y in between 0 and 1. At any point y in here, we slice it at that level. So I take this slice here, and I take that slice there, and I get this. And this thing is a slice of the thing that I spun around. This is two-dimensional, but this is like slicing out a level of that bowl kind of thing that we get. And so what is this going to look like? I'll draw it over here. And again, please forgive the drawing in advance. It's going to look like something like this. The whole point is that you get the general idea, and it's not going to be pretty, but we see that it's really not going to be pretty. I'm a man of my word about stuff like that. This is going to be gross, but we see what it's kind of going to look like. It's this disc with this tiny little width, right? It's like a flat disc that then or not disc. It's because it has the hole punch in it, but it's this kind of donut thing that then we raise up a little bit to give it a little bit of volume, and we'll talk about that in just a second. because this is one of the sort of subtleties of calculus. We'll talk more about this at the end of the video after we show how to do this. But this is similar to the way that we can envision integration in general in 2 dimensions, and we'll talk about that, how it relates to the fundamental theorem of calculus and everything as well. But right now, what I'm going to say is just this thing is going to have this infinitesimal width of dy, right? Just the way that when we integrate in 2 dimensions, we take we integrate over one variable, we integrate kind of like a bunch of lines, and we get an area. So 1-dimensional things, we get an area. Here, we're sort of integrating a bunch of 2-dimensional things and getting a volume. And so then we'll talk about that. So what we're thinking about here, is starting with these things right down at the bottom there, and then you slice. This thing kind of moves up. And sweeps out, as we say, sweeps out the volume. Here we get a little disk. And each one, and I'm thinking about this, and this is the part where it's the math analogy, not the actual reality of it. The reality is that we're taking limits of Riemann sums. Calculus is all about taking limits. But here I'm going to think about this again, so that I can visualize this thing and get a sort of conceptual grasp on it. I'm going to think about this as taking an infinite sum of these infinitely thin disks. I'm going to have this disk which moves up the thing and gets wider as we go, and then narrower to the top, and sweeps out the volume. And I'm adding up all of them. So and again, that is a math metaphor. It's not what's actually happening. It is not an infinitely thin disk. This dy that I throw in here that I say is its height. That's which sort of drags it into the 3rd dimension. Before it was just a 2-dimensional disk. Now it has this little bit of height, which gives it this infinitesimal volume. And these are the things that I'm going to be adding up. We'll talk in another video about the finer points of this that probably most people don't care about. What are infinitesimals? What are they not? They're not numbers, right? We can't multiply and divide by them. They represent infinitesimal quantities, limiting processes. We'll talk about that. Right now, we're thinking about it as an infinitesimal number, an infinitely small number, right? So that this thing is going to have an area and an infinitely small height, which gives it an infinitely small volume, and we add all of those up. And so, okay, so how am I gonna finally piece this integral together? Well, I'm going to think about this as adding up from 0 to 1. So starting out when y is equal to 0, I'm integrating with respect to y. That's why it's the dy and not the dx. Starting at 0, going up to 1. So those are the bounds of my integral. That's the first thing. And then what am I integrating? Well, I'm taking the area of each one of these things, the area at whatever point that is y, and we'll get this in just a second. That area, and then I'm multiplying it by the dy, and this is what they sometimes write as the dv, the infinitesimal amount of volume. I'm at every stage, at every height, right between 0 and 1, as I go up, slicing it, looking at what is that infinitesimal volume. That's the area at that point times the infinitesimal height, drags it into the 3rd dimension. So I have volume, and I can add them all up. And so again, thinking about this disk kind of moving up as y goes from 0 to 1, moving up and changing size, and we're taking this infinite sum of these infinitely thin disks. Just the metaphor, not what's actually happening. How do we find it though? How do we actually figure out what we call the cross-sectional area? Well, I have to look at whatever height the y is. So I look at right here, what is my y height, and what is the area in terms of y? So I'm going to get a formula for this that involves y. What is the area of the thing? And this is a terrible color. There we go. That makes it stand out more. What is the area of the thing at this height? Well, so this is this kind of donut shaped thing, right? It's not a disk. It's got the middle punched out. It's a circle, right? Or a disk is a filled in circle. So it's a disk with then a smaller disk punched out of the middle. So if I look at this from above, it's going to look something like this. It's this big disk with a smaller disk punched out. And so its area is going to be, I'm never going to get that perfectly centered, sorry. The area is going to be the area of the bigger disk minus the area of the little disk that was punched out of it. And so what is the area of the bigger disk? Well, it's pi, I almost wrote 2 pi r, oh my God, pi r squared. It's been a long day. And in this case, what is the r? Well, I have to look at what is the outer radius of this thing. So what is, and it's supposed to be blue. what is the outer radius of this? What is this distance? Well, it goes from 0 to the perimeter to the outer function, which on this interval is going to be the squared function. I'm going from 0 out to this point. And what is this point? Well, this is the point, the x coordinate, that corresponds to this y. And but I need that in terms of y. I can't throw an x in there. I can't say, well, my area is pi times x squared, because I'm doing an integral in terms of y. The bounds of integration are y from 0 to 1. The dy multiplied by an infinitesimal in terms of in y, an infinitesimal y, this infinitesimal change or height in the y direction. And so I have to get x in terms of y. But I can do that because I know this is a point on the squaring function. Y is equal to x squared. That means that x is equal to square root of y. So that means that the area here is the outer radius is square root of y. So this is pi r squared, which is pi times square root of y squared, which is pi times y. That's the outer radius here. What about the inner radius? Well, that's just the line y is equal to x. That's where it hits here, right? I go over there and down there. That's the line y is equal to x, is the inner boundary of this thing. So this distance is just going to be y, right? It is the x coordinate of this point, the distance over. I went over by x and up by y here, but that's the line y is equal to x, so they're equal. So the inner radius is actually just y. So I'm subtracting. I'll do it over here. I had pi times square root of y squared, and then I'm subtracting from it pi times y squared. The inner radius is y, and the outer radius is square root of y. And we're on this interval from 0 to 1, so it makes sense that the square root of y would be the outer radius, and y itself would be the inner radius. And so what do I do there? I get, this is pi times y minus pi times y squared. I can factor out the pi, and I get this y minus y squared, or this is pi times y times y times 1 minus y squared. However I want to do this. Okay, that is my area as a function of y. That's the cross-sectional area. And so the integral is done. The integral is done. I have, if I can duplicate this and bring it down here, I get the integral from 0 to 1 of the pi goes out front, and then I have y times 1 minus y squared dy. And as I do this, I'm realizing that I'm an idiot for factoring out that y, because we're taking an integral, and it's going to be easier to integrate it. If this is just the sort of math instincts to factor stuff, you got to fight that urge sometimes to just factor on without thinking, right? Factor first and ask questions later. It's going to be a lot easier to integrate like this, and that is my area. And with all of these things, I'm just gonna leave the actual integration, because I want the focus of these videos. I want the focus of these things to be on the process, on understanding this. And so just set it up. Like, for now, don't even solve it, just set it up. I don't want people muddying their minds with thoughts of actually computing integrals at this stage, right? This is absolutely like crushing for most people, trying to understand these things, trying to get your mind around how to set these things up when you have all these Riemann sums going on and this weird abstract stuff. That's why we're simplifying it and thinking it in terms of this disk moving around, sweeping out the area as it's sweeping out the volume as its area changes, and it has this infinitesimal height. That's why we're using this metaphor to sort of get a visual dynamic way of thinking about this. And so we want to do this over and over again. We're going to do more and more of these things where we look at more complicated examples with different functions and different axes and cool stuff like that. But every single time the focus is on just setting up the integral, figuring out where are the bounds, what is the cross-sectional area, how do I solve for them, how do I set things up, and then, because once you've done that, you can solve the integrals, right? We know how to solve integrals. And we have a bunch of videos on that where we look at techniques of integration and everything, and we will do the same kind of things. And those, if you understand how to do that, you can do this. But with these, please just focus on the actual setup, because that's the hard part. That's the part that most people just never understand, because it's taught in a way which makes it much harder to understand. And so we're going to have a lot more of these coming out very soon, where we do a lot harder ones. And by harder, I mean more fun, of course.